Okay, so welcome to Math 355, Section 1. This is Lecture 2. And so what I want to do today is talk about proof techniques. And we'll do a little bit of notation and terminology just so we have some things to talk about when we're doing proofs. But I really want to emphasize, how do we look at what we're trying to prove? How do we come up with a path? There is frequently more than one way to prove something. And after a while, you start to get a sense of what is the right way to attack a problem. You start to notice certain key features. One of the favorite examples I like to use is, imagine you have a newborn baby and the baby is crying. What can you do? You can pat the baby. Good. What else can you do? Give a pacifier. What else? Feed it. Change the diaper, which amazingly a lot of people forget. Change the diaper. There's lots of different things you can do. After a while, you start to recognize, oh, that's the I want to be held cry. That's the I want food cry. That's I have a need of a new diaper cry. And after a while, you have a sense, when you look at things, oh, here's the key feature. I've seen lots of problems like this. And when I've seen this, this is a good way to go. So the more problems you do, the more experience you have, the easier it's going to be to figure out how you should attack something. If you try to prove something and it doesn't work, try something else. Put that off to the side, take a new piece of paper, and then come back. So I'll talk a little bit about proof techniques today, especially proofs by induction. I'll also do proofs by story, which is one of my favorite techniques. A lot of these methods are very easy to follow if someone is guiding you through them step by step by step. But it's much harder to figure out, how did anybody ever come up with looking at the problem this way? Well, a lot of it is experience. The more things you do, the more you recognize certain key features. So the first is just some notation. So one-to-one, on-to equivalence. A lot of times in mathematics, we have multiple words for the same thing. So we talked a bit about this. So one-to-one or injective means if f of x equals f of y, then x equals y. What about the other direction? So this is saying that if the outputs are the same, then the inputs are the same. Is the other direction true? If the inputs are the same, then the output is the same? So if x equals y, will f of x equal f of y? If the inputs are the same, will the outputs be the same? So if I evaluate f at 5 and I evaluate f at 5, will I get the same thing? Yeah, that direction is easy. You could do this as an if and only if. F of x equals f of y if and only if. So we could do f of x equals f of y if and only if, which we often write IFF, if and only if x equals y. One direction here is really straightforward. If the inputs are the same, of course the outputs have to be the same because it's the same object. So we say that the function is injective or one-to-one if it satisfies this. It's onto or surjective if f is from, say, A to B, given any B in B, there is an A in A such that f of A equals B. What this is saying is, no matter what item you have in the output space, I can find something in the input space that goes to it. That's what it means to be onto or subjective. We'll often use the subroutines for there exists, and we'll sometimes use this as for all, just as a way to more concisely write notation and to just be a little bit faster. So I'll try to write it out in the beginning of the semester, but then very quickly I'll start shifting to math speak. Okay, then we're going bijection. If it is injective and surjective. So f of x equals x squared is a bijection from 0,2 to 0,4, but not from -2,2 to 0,4. And if you look at the plot of the function, see that except for x equals 0, you give me a value of y, and there's two values of x that go to the same value of y. So there's no way that this is going to be injective in general, unless I restrict my inputs. So if I look at all real numbers as inputs, it's not going to be injective. You know, I'm looking at the squaring function. -1 squared is the same as 1 squared. But if I restrict myself and I'm only looking at, saying, the non-negatives, so looking at the interval 0,2 to 0,4, then in that case, the function will be injective now. So a lot of times what you can do is you can take a function that's, you know, having some issues, and if you restrict where you define it, you can make those issues go away. Okay, so the last thing to talk about, I think, is equivalence. So we say something is reflexive if x is related to x. It's symmetric if x is related to y, then y is related to x. And it's transitive if x is related to y and y is related to z, implies x is related to z. So if you satisfy all three, we're called an equivalence. So can you give me an example of a relation that's an equivalence? So there's one really obvious one. If you think about it, this should of course be an equivalence relation. The equal sign, right? So if we take the equivalence to be equal sign, that's going to work. Is x equal to x? Yes. If x equals y, does y equal x? Yes. So the equal sign will immediately work. Can you give me a non-trivial example? So if you give me a non-trivial example, this is going to be a weakening of equality. So instead of saying two things are equal, we're going to say they're equivalent. So can you think of something? And we did talk about this last time. What kind of scalar multiple? So what kind of objects are x, y, and z? Okay, so you could say if x, y, and z are vectors, and they're scalar multiples, and that means they're in the same direction. So that would work. So multiples of vectors. But there's some more basic ones that we talked about yesterday. So if you think about the clock, what was 10 plus 5 on a clock? So on a clock, what would 10 plus 5 be? 3. So is 3 the same as 15? Yes, on a clock. So clock arithmetic. So clock arithmetic would be a great example of an equivalence relation. We're not saying 15 is the same as 3, but we're saying on a clock, we can't tell the difference between 15 and 3. For another example, we could do either less than or greater than. What do you think? Do you think less than or greater than would work? Well, I'm just saying, let's say less than. Let's say, can I do less than as my relationship? Do you think that's going to be an equivalence? Yes or no? So it's not symmetric. So less than would not work. What else does it fail? Yeah, it feels reflexive. So this is not symmetric, not reflexive, but it is transitive. So it is possible to have something that has some of these properties, but not all of the properties. So it's always good to get a sense of what are the possible objects that satisfy these conditions. And so if I give you something, reflexive, symmetric, transitive, if it satisfies all three, we call it an equivalence relation. And the way to think about an equivalence relation is for the properties we care about, they're indistinguishable. I can't tell the difference from one to another. Okay? So this is just some nice terminology that we'll be looking at throughout the semester. And one of the biggest examples of equivalence is going to be clock arithmetic. Is two numbers will be the same if they differ by an integer multiple of the number of hours on the clock. Okay, so what I want to now turn to is proofs by induction. So what I've done is I've written up some notes of these, and so the notes are going to be somewhat detailed on the slides so that you can hopefully just pay more attention and not worry about writing too much down. So I will always post the notes after class. It may take a couple of hours depending on how many administrative meetings I have. How many of you have seen proofs by induction before? Okay, so you can tell me if I'm going too slow or too fast. What I want to do is I want to cover just some basics of proofs by induction, and I want to apply them to some examples you've probably seen and maybe some examples you haven't seen, and try to emphasize what can go wrong when you try to do proofs by induction. So the general idea is you have some statement event and want to show it holds for all n. And what we could do is we could start trying to check for various values of n. Does n equal 0? Does it work? Does n equal 1? Does it work? But even if we check it a million times, that's a drop in the bucket compared to infinity. Now, the more times it works, the more confident we are that the statement is true. But I can give you some very strange statements that work for the first 40 values and then break down. And so you have to be extremely careful. We saw an example with 16 over 64 last time, but things can break down. So it's great to get evidence, but evidence is not proof. So what I want to do is just highlight some statements. So imagine your P of n is the statement, the sum of the first n integers is n plus 1 over 2. Have you seen this? The sum of the first n integers is n plus 1 over 2. Have you seen this one before? Okay, this is one of the most famous ones. So imagine, Pn is 1 plus 2 plus ... plus n equals n plus 1 over 2. We can try checking that for various values of n, and we can see it works. Now, in problems like this, there's always the question, do we start at 0 or do we start at 1? Well, if I'm summing, it doesn't really matter if I include the 0 or not, right? Do you want to include the 0 or not? Okay, all right, so now here is a direct proof. And the story, which it's required as a math professor that you have to tell, is when the great Gauss was very young and in school, he had a teacher who was just having one of those days and couldn't deal with the brats. So he told them, add up the numbers from 1 to 100, expecting, he'll have some time to just mentally regroup. And almost instantly, Gauss says, 5,050. And what Gauss's very clever idea was, is let's let S be 1 plus 2 plus ... plus n minus 1 plus n. Well, if I write the numbers in reverse order, it's still going to be the same sum. So if I add them, I get twice S is n plus 1 plus n plus 1 plus n plus 1. Each time it's going to be n plus 1. So and I have this n times, so it's n times n plus 1. Thus, the sum is n plus 1 over 2. So my students used to ask me when my kids were young, who do I love the most? And the answer was easy. It's always whoever slept better the night before. That was the defining property. There is more than one way to prove things. And it's not unreasonable to ask, so which method of proof do you prefer? This is a wonderful proof. This is a direct proof. It's very straightforward. The difficulty is it doesn't generalize well. If I wanted to do the sum of the squares or the sum of the cubes or the sum of the fourth powers, this method wouldn't work for that. This method works beautifully for sums of first powers, but it doesn't extend as nicely. That doesn't mean you can't play games and make other things work. You could play some games and make things work, potentially, but much harder. It's not nearly as clear. But if you want, try to do that. Try to see, can you somehow, knowing that this sum is n plus 1 over 2, can you use this to figure out a formula for the sum of squares? Can you somehow modify the trick and get everything to work? Okay, you might be able to. And so I will leave that as an exercise for you to think about. Is there a way to make that work? Okay. So we're going to talk about proofs by induction. So we can't check for every value of n. So we need a way to formally check all values of n in a finite amount of time. And that's how induction works. It works by basically a staircase. So what's going to happen is, I'm going to do one. I gambled that you would want to choose to start at 1 and not 0 when I made these notes. If you had said 0, I would have had to quickly change the 1 to a 0. So we will show that statement P1 is true. And then what we'll do is we'll show that whenever statement Pn is true, statement Pn plus 1 is true. And if we can do this, then we have Pn is true for all n. And it's going to, and I'll show this picture again later, it's going to work like a staircase. Here's n equals 1. Here is n equals 1 implies n equals 2. And now here's n equals 2. And then here is n equals 2 implies n equals 3. And then here would be n equals 3. And you just walk up the staircase. So if we know that whenever Pn is true, Pn plus 1 is true, and we know P1 is true, once we know P1 is true, we can then deduce P2 is true. Okay, so again, why is this going to work? Well, we have two pieces of information. We have P1 is true. We know the starting value is true. And we know whenever Pn is true, Pn plus 1 is true. Note that this is not saying that we've proven Pn is true. We're assuming Pn is true. And we're showing that if Pn happens to be true, imagine you knew P 1000 is true, then we would know immediately P 1001 is true. Okay, and so let's take n equals 1. So if we take n equals 1, then we know P1 implies P2. So if P1 is true, then P2 is true. So from these two statements, we can now deduce that P2 is true. Now what value should we take for n? Not P2. What value should we take for n? 2. And so now we take n equals 2. And this is a great example of search and replace. It's essentially the same slide, right? I now put in 2, and we know P2 is true. We know that P2 implies P3, so P3 is true. So what value do we take for n now? 3, right? And just, lather, rinse, repeat, we keep working. So P3 is true, P3 implies P4 is true. So now we know P4 is true, and so on and so on and so on. At this point, I'm bored. I'm not going to keep doing this. You just keep marching down. Okay? So this is how induction works. So, as I said, it's the staircase. We know P1 is true. P1 implies P2, so P2 is true. We know P2 is true, P2 implies P3, P3 is true, and so on and so on and so on. They sometimes also use like a domino image. The first domino knocks down the second, knocks down the third, knocks down the fourth, and so on and so on and so on. So all we have to do is prove two things. We have to prove P1, and then we have to show that if Pn is true, then Pn plus 1 is true. For a lot of problems, if you know Pn is true, the goal is when you look at the expression for Pn plus 1, you try to find Pn lurking inside it because you know what that is by the induction hypothesis. So we call the first step the base case, and the second the inductive step. Okay. So let's go back to the problem we had before. Let's look at the sum of the first n integers. Let's show it's n plus 1 over 2. So the base case is trivial. We first have to prove that P1 is true. And then we have to prove the inductive step, which is more work, that if Pn is true, then Pn plus 1 is true. Okay, so how would we do this? Well, the base case is very straightforward. All we have to do is show that 1 equals 1 times 1 plus 1 over 2. So 1 times 1 plus 1 over 2 is just 1. And so the base case follows immediately. Most of the time, the base case is not that hard to prove. Especially in expressions like this, you have a conjectured formula, you just substitute in. Now, if you're being extremely observant, you would notice that we have the claimed formula. If we didn't know what the formula was, it would be much harder to prove these results. There are ways to sniff out and figure out what these formulas are. I've actually recently written a paper with some students on how to do this. There are techniques you can use, but induction is a lot easier if you know what the answer is. If you know what you're trying to prove, that's a huge hint. So a lot of times in mathematics, we first do some explorations. We try to get a sense of what's going on. If you read any math textbook, you can be left with this incredible respect for the mathematicians as to, wow, how did they know how to argue? Precisely because you're only seeing the final product. You're not seeing all of the attempts that didn't work. You're not seeing all the things that they tried. And then they go back and then they try to figure out what's the best way to explain this? What's the best order to present things? So a lot of times we don't know what the answer is going to be. We spend a lot of time exploring first, gathering data, building conjectures. And then, oh, okay, now that I have a formula, let me see if that formula works. All right, so continuing with this problem, let's do the inductive step now. So we get to assume that Pn is true, and we must show that Pn plus 1 is true. So again, if we wanted to, we could check n equals 2, 3, 4, 5. We could do a bunch of n's to just build some more intuition and make sure that the formula is correct. It's not a bad idea to do at least a few more, because if there is a mistake, it's nice to catch the mistake before you do too much work. So let's assume we've done that and we see that the formula keeps working, and now we want to try to prove by induction. Okay, so we've done some extra steps. These checks are not necessary, but they do work. And so what does it mean for Pn to be true? It means that 1 plus 2 plus all the way up to n equals n times n plus 1 over 2. We get to assume that that's true for n. N is some arbitrary integer. We don't know what n's value is. We can just assume that that's true. And now what we want to prove is that 1 plus 2 plus all the way up to n plus 1 equals n plus 1 times n plus 1 plus 1 over 2. That's what we're trying to prove, given that the sum of the first n integers is n plus 1 over 2. So the question is, how do we proceed? How would we try to prove the statement Pn plus 1? Well, we know the statement Pn is true. Can you see the statement Pn somewhere inside Pn plus 1? Yeah, so basically the first n terms in what we're trying to prove for Pn plus 1 is just the statement Pn, and we know what they are by the inductive assumption. So what we can do is we can say, notice that it starts off with 1 plus 2 plus n. We are assuming that that equals n times n plus 1 over 2. So what we can do is we can take 1 through n and substitute n plus 1 over 2. And so when we do that, we get n times n plus 1 over 2 plus n plus 1. And so we just need to show that this equals our claim, n plus 1, n plus 1 plus 1 over 2. So is this clear how this goes? Have you seen this argument before, or is this new? You've seen this before? Okay, this is why I'm not going through excruciating detail. This is why I've converted this to just notes, because this is something you should hopefully have seen in a calculus class when they're trying to rigorously prove the fundamental theorem of calculus. Here's a way to test things by looking at sums of integers, squares of integers, and so on. So how do I add two fractions? What do I do? Common denominators, right? All that stuff from algebra 2 is now useful. So I want to add the two fractions. I get common denominators. So I multiply the second one by 2 over 2. And when I add, notice that they both have an n plus 1. I'm going to get n plus 2, but I can write n plus 2 as n plus 1 plus 1. So I'm just doing a little bit of algebra now to show that it equals exactly what I want it to equal. And so that finishes the proof by induction. And so we've now shown that the sum of the integers is n plus 1 over 2. If you had to, it's not that bad to show that the sum of the squares is n plus 1, 2n plus 1 over 6, because I'm telling you that this is what it should be. The proof is going to be almost identical. You first check the base case, do a few more cases just to be sure, just to double check. So we can do a few cases and see, okay, yes, it all looks like it's working. And then the proof is going to be almost identical. The only thing that's going to change is a little bit of the algebra. And so now when we look at the sum of the squares, well, we notice that the first n squares by the inductive assumption is just, n plus 1, 2n plus 1 over 6. So we just plug that in, and then we add n plus 1 squared. And so it's just about doing some algebra at this point. And the question is always, what's the best way to do the algebra? I know that we're going to have to add n plus 1 squared, right? So because we're going to have to add n plus 1 squared, when we look at the sum of the first n squares, I've already got an n plus 1. I know I'm going to add an n plus 1 squared. I know I can pull out that n plus 1. That's why I chose to do a little bit of algebra right now. Well, this seems to be like a typo here. This can't be right over here. Oh. It has dropped the squares in what's going on down here. And it's changed. Oh, that is annoying. So for instance, over here, this is, 2n squared over here. This is 2n squared over here. This should be a squared over here, and this should be a plus sign over here. This should be an n squared. So on my computer, it came out fine, but when I transferred it to the iPad, it changed the superscripts there, but it did not change the superscripts in the other places. Interesting. All right, so when we just add everything together, we pull out the n plus 1, we do the algebra, and everything works out fine. Do you think you could come up with a proof for the sum of cubes? What do you think?
Do the same thing.
Do the same thing. But what would make it a lot easier to come up with the proof? What would I have to give you to make your life easy? Yeah, I'd have to give you the formula. Now, the other thing is, if you believe that it is a formula like this, that it's some polynomial, how many points do you need to determine a line? 2. How many to determine a parabola? Cubic. 4. And so when I'm looking at sums of squares, it's a polynomial of degree 3. When I'm looking at sums of first powers, it's a polynomial of degree 2. If I'm looking at cubes, maybe I believe it's a polynomial of degree 4. And so if I figure out 5 values of n and what the sum is, that might allow me to guess what the polynomial is. And there are ways to make this formally correct. And at this time at the end of today, I'll talk a little bit about that. So there are ways to come up with what you should try to prove. All right. So the last one I want to do is just another proof by induction, but to mention that sometimes induction is not the best way to go. So if you look at the sum of the squares of the odd numbers, it turns out the sum of the squares of the odd numbers is a perfect square. So if I look at the sum of the first n odd numbers, it's n squared. So you always want to be careful about the notation you use. How do I write things down? And so you can write a general odd number. Do I want to go up to 2n plus 1 or 2n minus 1? Well, if I do 2n minus 1, if I take n equals 1, I just have one term. If I take n equals 2, I go up to 3, I have two terms. Oh, okay. So if I write my final odd number as 2n minus 1, then I have n odd numbers. That's why I've chosen to write things this way. And the claim is that if you sum the first n odd numbers, you get n squared. Well, we can check if n equals 1, does 1 equal 1 squared? Yes. We don't need to, but if we try to check n equals 2 and n equals 3, would that work? Yes. 1 plus 3 is 4, which is 2 squared. 1 plus 3 plus 5 is 3 squared, which is 9. So now I'll leave it to you to prove this by induction. I will give you a non-inductive proof. I'm going to draw the dots in a nice way. So, trying to use color to make things as easy as possible to visualize. So if I have just one odd number, it's one dot. If I have 1 plus 3, I add 3 more dots, and notice that I'm adding it in such a way to get a square. And how many dots do I have to add? Well, I had one dot, so I need one dot below, one dot to the right, and then one dot in the corner. Now I have a 2 by 2 square, and I need to add more dots. How many dots do I need to make a square? I have to do 2 more for the 2 columns, 2 more for the 2 rows, and then 1 more in the corner. So instead of adding 3 dots, I'm going to add 5. And you can just keep seeing how you're going to match. And then the next time, I'm going to take how many dots I had, and I'm going to have to add 2 more. Every time I have to add 2 more dots to get a square. So as a nice exercise, try to make this rigorous. But a lot of times in mathematics, when you see something that looks nice, there might be a big reason behind it. The fact that it's a square suggests maybe there's a geometric argument going on as to why the sum of the odd numbers is n squared. We can do it formally by induction. We can just manipulate symbols. But we're missing something when we do that. We're missing that there's more at play here. Okay. Any questions about this proof? So this is a nice one. All right. I won't go through the details of this one. I'll just leave this one. This is a little bit more difficult one. 133 always divides 11 to the n plus 1 plus 12 to the 2n minus 1. All right. So I'll leave this for you to think about. The solution is going to be in the slides. Just turn away your eyes for just a second. This way, just for the video, it's actually there as well. Okay. Before going on to the next subject, a lot of times we can't prove something, but we can still get a feel for the answer. And this is an extremely valuable technique to get. You want to have a sense of what the answer should look like, and then that way when you're trying to prove things, wait a minute, that doesn't look at all like my intuition is saying. So let's say we believe that the sum of the first n integers is n plus 1 over 2, that's n squared over 2 plus n over 2. So when n is really large, what does that sum look like? Approximately, what does the sum look like when n is large? N squared over 2. When n is very, very large, the n over 2 doesn't really matter. This is like telling Elon Musk or Jeff Bezos, we made a mistake. Your net worth is actually $1 million less than we thought. It's not going to really be that noticeable. For most of us, it will be. If it's not, please talk to me after class. Can you give me an upper bound and a lower bound for this sum? And I don't care if it's a bad upper bound or a bad lower bound. Can you give me some kind of upper bound or lower bound? It's okay if it's a really bad lower bound or a really bad upper bound. What's a really bad lower bound? Simplest lower bound you can think of for the sum. I'm sorry? 0. You can do a little bit better than 0, but 1. The smallest term is 1. So the lower bound is at least 1. Can you give me a better lower bound? 2, n. And so you can go all the way up to n as a lower bound. How about an upper bound? N squared. Because we have n terms and each term is at most n. Right? So we know that this sum is somewhere between n and n squared. Unfortunately, n and n squared are very different sizes. So the lower bound isn't close to the upper bound. But we do know, n plus 1 over 2 plus n plus, this is where things get annoying. If we look at just the last half of it, something like this. I'll put it in quotes. If we just take the last half of the sums, and then I think technically it should be one more than that. So I'm just looking at the second half. I have 1 to n halves plus 1 onward. Well, n might not be even, so I don't necessarily have n halves. Is it clear what I'm talking about? This the last half. This is the last half of the summons. How many summons do we have? N over 2. And each is at least what? And so that's n squared over 4. So this tells us that the sum is at least n squared over 4, at most n squared. Oh, okay, so now order of magnitude, we know it's of size n squared. So even if I don't know exactly what the sum is, I know it's going to be like n squared for large values of n, up to some constant. And it's really good to be able to get a feel for your sums and for your answers. Okay, so I'll skip doing those slides because we just did that by that. All right, so the following is one of my favorite false proofs by induction. I'm going to prove everybody in the world has the same name. To do this, I need at least one person here to have a valid student ID or driver's license. Does one of you have that? Right. Just make sure. Okay. Now, there are multiple people in this room. According to this proof, it doesn't really matter whose ID I check because we're all named the same. So everybody is named Katie, and I'm going to prove that now. Okay, I'm going to prove it by induction. Does anybody think I'm going to be able to successfully do this? So you're skeptical. So try to find where there's a mistake. So here's my statement. Pn is the statement. In any group of n people, everyone has the same name. Now, I'm not saying that if I have 2 different groups of n people, it's the same name in each of those groups. I'm saying whenever you have a group of n people, everybody in that group has the same name. So we're clear on what the statement is. So the base case is in any group with 1 person, everyone has the same name. Do you agree that the base case is true? Why? Good. You're just 1 person, so everybody has to have the same name. So now we get to assume that in a group of size n, everyone has the same name. And now we want to show in a group of size n plus 1, everyone has the same name. All right, so the base case follows immediately, as we said. So let's prove the inductive step. So I went online and I downloaded some stick figure images. So here is a group of n plus 1 people. And we get to assume that in any group of n people, everyone has the same name. Can somebody give me a group of n people from this set of n plus 1 people. So you have to give me a group of n people from these n plus 1 people. There are two natural choices for groups of n people from n plus 1 people. Can someone give me one of those natural choices? You have to tell me which n people are in your group. Except for, well, we don't know who the age of people, but give me a procedure to choose n people from these n plus 1 people. Choose. I'm sorry? Well, I'm trying to prove everyone has the same name. You have to give me a way to choose n people. They're labeled 1, 2, 3, and n plus 1. So give me a set of n people. First, choose the first n people. They all have to have the same name. And so somehow things have, okay. So all the first n people have the same name by the inductive assumption. Give me another group of n people. So we did the first n, the last n. And so if I do the last n, and see, it seems like things have resized. All right, so we'll take the last n, and they all have the same name. Now, this is where things get interesting. Notice that if I look at the two groups, there's a lot of people in common. The second person is in both groups. The third person is in both groups. The fourth person is in both groups. The nth person is in both groups. Everybody in the first group has the same name as person 2. Everybody in the second group has the same name as person 2. Therefore, 1 has the same name as person 2, and n plus 1 has the same name as person 2, so everybody has the same name. And given that we know somebody in this world is named Katie, everybody must be named Katie. What's wrong with this? Well, but by induction, I can assume whenever I have n people, they all have the same name. The first group is people is 1 through n. By the inductive assumption, they all have the same name. So 1 to n all has the same name. I don't know what name that is, but 1 through n all have the same name. And then 2 through n plus 1, that's another group of size n. They all have the same name. I can't. That's a group of n people. The statement says any group of n people have the same name. This doesn't matter that they're different groups. Each group, there is one name for the people in group 1. There is one name for the people in group 2. Since person 2 is in both groups, since person 3 is in both groups, since person n is in both groups, everybody in group 1 has the same name as person 2. Everybody in the second group has the same name as person 2. So whatever the name is for group 1, it's whatever person 2's name is. Whatever the name is in group 2, it's the same as person 2's name. So person 1 and 2 have the same name. Person 2 and n plus 1 have the same name. So everyone has the same name. Does n have to be what? What do you mean by ordered? Yeah, we're just going up by 1. The inductive assumption is you assume Pn is true, and you get to use that when you study Pn plus 1. So it looks like everybody has the same name. Okay. And so what is going wrong here? So what's going wrong here is imagine n equals 1. If n equals 1, then n plus 1 equals 2. And the first group only includes person 1. The second group only includes person 2. When I was saying there's an overlap, there is not an overlap if n equals 1. If n equals 2, yes, there's an overlap. So imagine you knew that in any group of two people, you always have the same name. Then everybody has to have the same name. It's a broken staircase. P1 is true. P2 does imply P3, but we don't know P1 implies P2. We accidentally assumed some properties of n. Because it's like, oh, come on, the small values are clearly going to be true. Let's look at what's going on when n gets really, really large. No, we have to be careful for all values of n, even the small values. And the difficulty here is we do not have n equals 1 implies n equals 2. There's no overlap. So when I was drawing these pictures, these were deliberately misleading pictures. I was assuming some properties of n when I drew these. I was assuming that n was at least 2. And we don't know that n is at least 2. There's a whole slew of bad things you can, well, not bad things. There's a whole slew of incorrect proofs you can give using methods like this. I can prove every integer is the square of another integer by arguing along these lines. It's amazing how many things you can prove that are false. But if you think about this problem, it makes sense that if every group of two people have the same name, because if you have 3 people, 1 and 2 have the same name, 2 and 3 have the same name, so 1 and 3 have the same name. We can use 2 as the link. We just don't know that every group of 2 people have the same name. And that's the difficulty. Okay, any questions on proofs by induction? So this is one of our key techniques to prove things. If you continue in mathematics, proof by induction is going to be one of the things you really need to know how to do. And so, I deliberately did not do one of the examples, try to do it, and then the solution is in the slides. So if you want to see the solution, you go through that. You can also, of course, talk to me, talk to the TA. Okay, I want to talk briefly about Pascal's triangle. So have you all seen Pascal's triangle?
Yeah.
Yep. If you have a good calculus class, they actually talk about this in trying to calculate the derivative of x to the n. And so if we want to expand things out, if we want to expand out x to the n, Pascal's triangle becomes very useful. So basically, each number is the sum of the number above to the left plus above to the right, and it's ones going down diagonally. Okay. And so if you take x plus y to the n and you expand it out, x plus y to the 0, anything to the 0 is just 1. There's only one quantity to the 0 that may not be 1. Does anybody know what that one quantity to the 0 is that may not be 1? Yeah, 0 to the 0. It's unclear what that is. It depends how you calculate. X plus y to the first is just 1x plus 1y. And that's the second row, 1, 1. Or if you want, the second row is really the first row. And the first row is really the 0th row. X plus y squared is 1x squared plus 2xy plus 1y squared. That's the row 1, 2, 1. And so on and so on and so on. Okay. I always forget, what time does this class end? It's 45. Okay, so I thought. Okay. And so on and so on and so on. So x plus y cubed is 1x cubed plus 3x squared y plus 3xy squared plus 1y cubed. We can keep going and going and going. And then just one way of defining Pascal's triangle is it's the coefficients that come when you expand x plus y to the n. Now, it turns out that there are explicit formulas for these coefficients, and they have a tremendous number of properties. There's a lot of identities. So I've already remarked 6 is 3 plus 3, 15 is 10 plus 5. Let's go diagonally. What's 1 plus 3 plus 6 plus 10? 20, which is the number down to the right. What's 1 plus 2 plus 3 plus 4? This is the hockey stick identity. If you go down diagonally to the left, the sum is just go down one more row to the right. So, there's a lot of beautiful, beautiful results about what these sums are. Okay. So the big identity is Pascal's identity, that each element is the sum of the number above to the left plus above to the right. And we'll prove that, and we'll prove that probably multiple ways because this is just such an important result. All right, so here is one way to possibly prove things. And let's just get some intuition. Let's say we know x plus y to the fifth. We've multiplied everything out. We want to calculate x plus y to the 6th, and this is why you do things with slides. And so fortunately here, it did not subscript the exponents. Did not remove the subscript from the exponents. Good. So x plus y to the 6th is just x plus y times x plus y to the 5th. Well, I can use the distributive law. That's x times x plus y to the 5th plus y times x plus y to the 5th. I then expand out what x plus y to the 5th is, and I multiply the first one by x and the second one by y, and I add the stuff. And if you notice, I'm deliberately shifting things when I add so that things with the same powers of x and y are directly underneath. And then when I add, you can see, oh, look, I've got x to the 6th, I've got 5 plus 1, x to the 5th, y, 10 plus 5, x to the 4th, y squared. You can see the fact that you're summing above to the left plus above to the right when we're looking at this. You can see where it's coming from. It's coming from the previous row when I multiply by x versus multiplying by y. It's just shifting a little bit over. Every time I increase my power of y, I'm walking one more step to the right. And that's why when I'm adding, I start off with one number, and then the next number is the number in that row, just one step further to the right. You can make this more rigorous, and you can say, let's say we have our expansion, and then we want to calculate the next one. All right. So we could prove it directly, but there's other ways to do it. So again, here is Pascal's triangle. And if I want to expand things directly, I could say, let's assume we know that x plus y to the n, let's say we know it's the sum, k goes from 0 to n. I'll write it as a n k, x to the k, y to the n minus k. And then x plus y to the n plus 1 would be x plus y times the sum, k goes from 0 to n of xk, y to the n minus k. And then by definition, that would be the sum. I'll use a different one. I'll use L equals 0 to n plus 1. I dropped the k's. The a's. A and k. This would be a n plus 1 L, x to the L, y to the n minus n plus 1 minus L. Is you could go through and try to do the argument we just did when n equals 5, and just try to do this in general. And I have x plus y times that, and you'll see that you're going to get some kind of story and relationship between the two. So as a nice exercise, I urge you to try to do this. Okay, you learn a lot more by trying, failing, and trying again. All right, so let's do some other proofs of this. Sum k goes from 0 to n. Choose k, x to the k, y to the n minus k, where n choose k is n factorial over k factorial, n minus k factorial. Has everybody seen these combinatorial coefficients? This is the number of ways to choose k objects from n when order doesn't matter. And here's the proof. So look at x plus y to the n. It's x plus y times x plus y times x plus y. Have n factors. For each factor, I either choose an x or a y. So the highest power of x I could get is if I choose x every single time, and that will give me an x to the n. The highest power of y is if I choose y every single time, and I would get a y to the n. Whatever power of x I have, the power of y has to be such that when you add those two together, you get n. So if n equals 10, if I choose 3 x's, how many y's do I have to choose? So if n equals 10, if in 3 of the 10 factors I choose x, and how many factors do I choose y? 7. So something of the form x to the k, y to the n minus k. If I choose xk times, I have to choose y n minus k times. So I know it has to look something like that. And now I just notice that how many ways can I choose k of the factors to be x? I have n factors. I have to choose k of the n factors with order not mattering. That's just n choose k. So as soon as you've defined n choose k to be the number of ways to choose k objects from n when order doesn't matter, it tells you that that's going to be these numbers. And now you want to prove that n choose k plus n plus 1 choose k is n plus 1 choose k plus 1. So I want to do it. Oh, sorry. Wrote it wrong. So this is the Pascal identity. This is what we want to do. We want to prove that n choose k plus n choose k plus 1 is n plus 1 choose k plus 1. That's basically that your number above to the left plus your number above to the right equals your number. There are many ways to prove things in life. One way is brute force. I can look at n factorial over k factorial n minus k factorial plus n factorial over k plus 1 factorial n minus k plus 1 factorial versus n plus 1 factorial over k plus 1 factorial n minus k factorial. Do you think it's going to be hard to show that these are equal? What would you do to show that they're equal? Make the common denominator. So just multiply through by a lot of things, do algebra. I don't want to do this. That's not the type of algebra that this class is. This class is abstract algebra, not direct, painful, tedious, boring algebra. But it's not bad for you to try to do that. And it will give you an appreciation of other ways of looking at things. So I urge you to just go through and show that you can make it work by brute force. But when you do the brute force proof, you have no idea why it's true. Right? You just know that the result is true, but it's not really meaningful. So let's do a more meaningful proof. So claim n choose k plus n choose k plus 1 equals n plus 1 choose k plus 1 by story. I need a great school, an awesome school. This is a marshmallow question, guys. Williams, all right? Let's say we have n students from Williams. And I need a school that sucks. Amherst. And we have one student from Amherst. And I want k plus 1 students. And so I want to choose k plus 1 students from a group that has n Williams students and 1 student from Amherst. Does everyone agree that the number of ways of doing this is just n plus 1 choose k plus 1? I have n plus 1 students total. I need to choose k plus 1 students. Does everyone agree that this is the number of ways to choose k plus 1 students from n plus 1 students? Yes? Okay. Now, let's break it up into 2 cases. So case 1, we have 1 student from Amherst. We have no students from Amherst. How many ways can you have one student from Amherst. Well, I have to choose the student from Amherst. There's only one student from Amherst, so I have to choose them. That's one, choose one. There's n students left. They're all from Williams. How many must I choose? Okay. Now imagine I don't have the Amherst student. So it's 1, choose 0. I don't choose the Amherst student. How many students must I choose from Williams? K plus 1. And there's the proof. We've just proven Pascal's identity. Much better than doing things by brute force. Notice that the tops always add up to n plus 1, and the bottoms always add up to k plus 1. Why don't we write it like this? Why do we write it as n choose k, not as 1 choose 1 times n choose k? What can you tell me about 1 choose 1? Yeah, they're all ones. We don't bother writing them. So a lot of times in mathematics, when you drop things that are 1, it can actually make it much harder to understand what's going on. When I write it like this, I have a much better sense of why the formula is true. It's 1 choose 1 n choose k plus 1 choose 0 n choose k plus 1. That's what adds up to n plus 1 choose k plus 1. Okay, so these are just some ideas of proof techniques. Okay. There's a lot of fun stuff you can do with Pascal's triangle. One of my favorites is imagine, since we do clock arithmetic a lot, whenever you have an odd number, put a dot. Whenever you have an even number, remove the dot. So this is what would happen if you have just one row, it would just be one dot. If you have 4 rows, it would be a triangle with a dot missing in the middle. As we do a little bit more, it starts to get interesting. I eventually rewrote the program. I initially did the program with the triangle rotated 90 degrees. It was just easier in Mathematica. Since then, I've decided it's better to do it the other way, but I haven't updated the slides. Where it now goes, you can actually play the video and see more and more rows being added. And you can see a fractal structure emerging in Pascal's triangle. The point of this is to just show you that things that you've seen many times, there's often additional layers to be gleaned from further analysis. And that leads in beautifully to the last topic for today, trying to get a sense of what to prove. So imagine you are the supreme power in the universe. And you first create the heavens and the earth and all that stuff, and you see it's good. And then eventually, I don't know what day, you decide to create calculus. And if you were going to create calculus, what would you choose as your product rule? The derivative of a product is what would you make the derivative of a product? What would you make the derivative of a quotient? The derivative of a product would be the product of the derivatives. What would the derivative of a quotient be? The quotient of the derivatives. It's not that way, right? That's not what the product rule is. The product rule and the quotient rule are a lot more complicated. So one of the big challenges in math is trying to figure out what to prove. When you have a book and the book tells you, prove the following, well, it's really not that hard to figure out what you're trying to prove. The book tells you, prove this. One of the things you need to learn is, how do you come up with what to prove? Well, we want to study the derivative of products. I need functions a of x, b of x, and c of x equals a of x times b of x, where I can take all of these derivatives easily. Can somebody give me a function which is easy to differentiate? X. Give me another function that's easy to differentiate. 2x. Although 2x is very similar to x in that it's just a scalar multiple. So instead of 2x, x squared. So we could do x and x squared, or more generally, we could do x to the n, x to the m. And you can argue as to, do we know this only when n and m are positive integers? Do we know them for real numbers? And then the product would just be n plus m. Okay, so if we do this, what is a prime of x going to be? Oh, I just realized, do you want to use a, b, and c, or do you want to use f and g? Fine, okay, good. What would a prime of x be? Technically, it's times 1, right? But the times 1 doesn't, when you're doing the chain rule, the times 1 will matter. But right now, it doesn't matter if we're going to drop it. What's b prime of x going to be? It's going to be mx to the m minus 1, and c prime of x will be n plus m, x to the n plus m minus 1. So the derivative of a of x, b of x involves perhaps a, b, a prime, and b prime. Seems reasonable. If you take b of x equals 1, we know a prime comes into play. And in fact, it would then be a prime multiplied by b. So you can look at special cases. You can look at a of x or b of x equals 1. Does it make sense that the derivative should involve a, b, a prime, and b prime somehow? Now, can you give me a way to get a power of n plus m minus 1 involving a, b, a prime, and b prime? How can I get that power? So a and b prime, and what else? Yeah, notice a prime x, b of x, and a of x, b prime of x, something times x to the n plus m minus 1. In fact, a prime of x, b of x, plus a of x, b prime of x equals c prime of x. This is not a proof that the derivative of a product is a prime b plus ab prime, but it is suggestive. And this is a way to sniff out the product rule by looking at some specific examples. This is not a proof. And maybe the product rule is more complicated if things are not polynomials, but if things are polynomials, things reduce really nicely. That's possible. But this is at least telling me it's probably more complicated than a prime b prime. I can see a prime b prime does not work here. Okay. But a prime b plus a b prime, that has a chance. And by using general powers n and m, I could have done x and x squared. But this now gives me infinitely many tests all at once. They're all very similar tests, which is disappointing, but it still gives me infinitely many tests. So the question is, are there any other functions where we know the derivative of the product? And if you remember your trig, there is. Let's do a of x is sine of x, b of x is cosine of x, and then c of x is sine of x, cosine of x. Does anybody remember a nice way to simplify sine of x, cosine of x? Well, a nice way to rewrite that product. You have to remember your trig. So let me multiply by 1. It's the same as 1/2 2 sine x cosine x. Does anybody remember what 2 sine x cosine x is? It's a double angle. So this is just 1/2 sine of 2x. So I'm assuming we know the trig derivatives of the basic function. The derivative of sine is cosine. The derivative of cosine is negative sine of x. The mnemonic I like to use is you have to remember where to put the minus sign. The minus sign goes with negative sign. And now, what's c prime of x going to be? It's 1/2, derivative of sine is cosine 2 of x, and then the derivative of 2x is 2. So it's just cosine of 2x. And so now, if we test a prime of x, b of x, whoa, so I'll change the pen, b of x plus a of x, b prime of x. That's going to be cosine x, and then b of x is cosine of x, and then a of x is going to be sine of x, and b prime of x is minus sine of x. Does anybody remember what cosine, cosine, minus sine, sine is? This is just cosine of 2x. This is another trig identity, which is c prime of x. So assuming we actually know what the derivative of sine and cosine are, assuming we know some trig identities, this is a verification of the product rule. Have I proven the product rule? No, but this is a lot more evidence in support of the product rule. Okay. If anybody is interested, this would be a really nice math outreach article to write. And I'm happy to have you do stuff like this as opposed to some of the more standard homework problems. Here is a way to try to gain intuition as to what the product rule should be. Let's look at a couple of examples where we can compute the derivative of the product and compare, and this builds up our intuition. I will just end with an aside. Is everybody familiar that primes are really good because you can write numbers uniquely as a product of primes? Yes. If I give you the function cosine squared of x, how could you factor cosine squared of x? How could you write that as a product of functions? Cosine x times cosine of x. But it's also the same as 1 minus sine squared of x. And how can you factor 1 minus sine squared x? Yeah, 1 plus sine of x times 1 minus cosine of x. I'm sorry, 1 minus sine of x. And so all of a sudden, and this is something we'll see more throughout the semester, things that held for the integers don't necessarily hold for generalizations. One of the big themes of this course, looking at groups and rings and fields and all these structures, is we want to take the integers, the rational numbers, the real numbers, things that we know, and we want to try to generalize them in other settings. And then the question is which properties hold and which properties don't. One of the things that's really nice about the integers is we have unique factorization. If I look at these, instead of integers, if I now have things in terms of functions, I have cosine x times cosine of x is 1 plus sine of x, 1 minus cosine of x. Cosine of x does not divide 1 plus sine or 1 minus cosine. So in terms of how do you factor things in generalizations of them, gets really strange and interesting. Okay, so this is a good place to stop for today. On next class, which is Thursday, we will now start the semester in earnest. And just stop recording.